Hello, this is DVKT Math, and in this video I'm gonna show you how to find the semi-derivative or the 1/2 derivative of 1 over 1 minus x. So this the 1/2 here, like normally you would see like first derivative, second derivative, or third derivative, etc. But well, there's also 1/2 derivative, pi-th derivative, or like eighth derivative. That sounds weird. Eighth, never mind. Or like 3/4 derivative. Um, well, 7/6 derivative, something like that. Anyway, so the orders of the derivative don't have to be integers, and they can also be fractions or like any real numbers or maybe even complex numbers. And well, in this video I'm going to show you how to find the 1/2 derivative of 1 over 1 minus x. So let's move on to the solution of this thing right here. Alright, I'm going to erase those marks. So here we're using what's called the Riemann-Liouville fractional derivative definition. Riemann-Liouville, I don't know if I'm pronouncing it right, but I guess it's Liouville. That sounds French. I don't know French. Anyway, so Riemann-Liouville fractional derivative definition for alpha between 0 and 1. This is the definition of Riemann-Liouville fractional derivative definition for alpha between 0 and 1, which says the alpha derivative of f of x, any function f of x, is equal to 1 over gamma of 1 minus alpha. The gamma here is the gamma function, the famous gamma function, times the derivative. So here we have the normal first order derivative here, times the derivative with respect to x, d over dx, of the integral from 0 to x of f of t over x minus t to the power of alpha, and then dt. So that's the Riemann-Liouville, I guess, Riemann-Liouville fractional derivative definition. Yeah, for alpha between 0 and 1. For the larger alphas, like for example, let's say for alpha larger than 1 and less than 2, then, let's say we're finding the 3/2 derivative, then you can do like find a 1/2 derivative first and then differentiate it once with the, the normal first order derivative, because 1 plus 1/2 is 3/2, something like that, or, there's, well, not, but there's a kind of like a broader definition for the Riemann-Liouville fractional derivative that kind of like includes alpha in all ranges. But in this case, we only need for alpha between 0 and 1 anyway. So yeah, for alpha between 0 and 1, this is the definition for the Riemann-Liouville fractional derivative. Alright, and then we're gonna use that definition to find the eraser. Sometimes this just doesn't work really well. Anyway, so, well, we're finding the 1/2 derivative, the semi-derivative, or the 1/2 derivative of 1 over 1 minus x. So the order of the derivative is 1/2. We're gonna let alpha is equal to 1/2, 1 over 2, and the function that we're trying to, find the semi-derivative is f of x equals 1 over 1 minus x. So we just substitute those things into the equation here, to this equation. I'm gonna box this thing. That looks too bad. Yep, this is better. Alright, anyway, so we're substituting, we're letting alpha is equal to 1/2, 1 over 2, and f of x is equal to 1 over 1 minus x. And we get this equation right here. Alright, so the 1/2 derivative of 1 over 1 minus x is equal to 1 over gamma of, well, 1 minus alpha. Alpha is 1/2, so 1 minus 1/2 is just 1/2, and then we get 1 over gamma of 1/2 or 1 over 2, and times the d over dx, the first derivative with respect to x, of the integral from 0 to x of, well, here f of x is equal to 1 over 1 minus x, right? So here we have the integral from 0 to x of f of t over x minus t to the power of alpha, and f of x here is 1 over 1 minus x, so f of t is just 1 over 1 minus t, 1 over 1 minus t, and well, and then over x minus t to the power of alpha. Here alpha is 1/2, so square root x minus t. So that's just substituting alpha equals 1/2 and f of x equals 1 over 1 minus x using the Riemann-Liouville fractional derivative definition. I hope I'm pronouncing it right. Liouville, I don't know. Anyway, so, well, so now the problem is, now this problem of finding a fractional derivative is, wait, did I introduce the word fractional derivative? I don't think I did. Anyway, so, these kind of like non-integer orders of derivatives are kind of like a part of a branch called fractional calculus, and this is a fractional derivative. The 1/2 derivative is a fractional derivative. Anyway, so, well, now the problem of finding the fractional derivative becomes a problem of solving an integral. So, well, this integral should be easy to solve, and after we substitute t to x minus t. Wait, something seems a little bit wrong. It's not wrong. Never mind, my bad. It's not wrong. So after we substitute t to x minus t, then we get this. Well, substituting t to x minus t is like substituting t equals x minus u. It's just that I don't want to use a new variable. Like, yeah, it's a simple substitution anyway. It does, like, the d doesn't really change. Well, it becomes negative, but anyway, so we after substituting t to x minus t, then we get this integral right here. This integral in the equation 1, this integral that I'm underlining so thick right here, is equal to the integral from 0 to x of 1 over square root of t times 1 minus x plus t dt. And so now to solve this, well, I'm gonna erase this first. To solve this, we're gonna substitute here, we're gonna substitute square root of t to t. This is just like substituting, again, this is just like substituting u equals square root of t, but I just don't want to use a new variable. So yeah, substituting square root of t to t, we get this integral right here. And well, this integral should be easy to solve because, well, you just use the inverse tangent, the arctan. So after solving that integral, you will get this. You will get the integral is gonna be equal to 2 over square root of 1 minus x times the inverse tangent or arctan of square root of x over square root of 1 minus x. So that's the result of the integral on the right hand side, this integral here. So that's the result for the integral. And now we're gonna use a trigonometric identity, not really an identity, but after drawing out the triangle stuff. So, well, we're gonna use this identity, arctan of square root of x over square root of 1 minus x is equal to arcsine, the inverse sine of square root of x. So, well, some of you might be confused at this identity, so I'm gonna explain it with more detail. So before going to the next solution slide, I'm gonna go to a white background to okay, I'm gonna draw out something here. And well, let's say this side is square root of x, this side is square root of 1 minus x. Sorry for the bad handwriting. I'm just not so used to writing on the phone screen with my hand. So yep, this is let's say this angle is theta. That's so bad though. That looks better. Anyway, so let's say we have a right triangle here, right? And then the angle theta, and then this side is square root of x, and this side is square root of 1 minus x. And well, what does the arctangent of... Oh, that looks so bad. And I missed the C. Well, the arctangent, the inverse tangent of square root of x over square root of 1 minus x is gonna be equal to this theta right here. Alright? And then, well, so now we have arctangent of square root of x over square root of 1 minus x is theta. That means, well, tangent of theta is square root of x over square root of 1 minus x. And then what is this side? This hypotenuse. Well, that's easy to find, and that's x. Just use the Pythagorean theorem. The square root of x, everything squared, plus the square root of 1 minus x, everything squared, is x squared, and then take the square root of that is x. So the length of this hypotenuse right here, wait, no, that's 1. That's not x. Bad math. That's 1, not x. Yeah, because square root of x, everything squared is x, and then plus the square root of 1 minus x, everything squared is, well, 1 minus x. So x plus 1 minus x is 1. Square root of 1 is 1. We're only taking the positive one because it's the length side of a triangle. Anyway, so using the Pythagorean theorem, we get the hypotenuse length is 1. So now, theta here. Alright, so we have arctangent of square root of x over square root of 1 minus x is theta. And we know the sine of theta. Sine of theta is equal to, well, it's equal to square root of x. So theta is equal to arcsine, inverse sine of square root of x. Sorry for the bad handwriting. I hope you can read it. Anyway, so that's why the arctangent of, well, I'm going to use a different color. That's why the arctangent of square root of x over square root of 1 minus x is equal to arcsine of square root of x. So anyway, I'm gonna go to a new background, a new white background, and go to the next slide of the solution. Alright, so yep, this is the result for the integral. I'm gonna get back to red because I like red better for some reason. Anyway, oh, that was bad. Yeah, and well, so here is the result of the integral after, well, evaluating it by 2 substitutions and then using the identity arctan of square root of x over square root of 1 minus x is equal to arcsine of square root of x. And well, that simplifies a lot. So this is the result of the integral, and after we substituting it into the original equation, well, I'm gonna go back to the first slide for a moment. So this is the original equation. Oops, where is the red? Alright. This is the original equation. So we solved the integral. So now we're gonna substitute the result into this equation that I'm boxing in red right here. So now I'm gonna go to the second slide. Back to the second slide. And well, so we're gonna substitute this result into that equation, and using the special value here, gamma of 1/2 is equal to square root of pi. So after we substituting the result for the integral and using this special value for the gamma function, we get our final answer is this, right here. The semi-derivative of 1 over 1 minus x is 2 over square root of pi times the derivative with respect to x, the first derivative with respect to x of arcsine of square root of x over square root of 1 minus x. And here at this step, it's just some tedious algebra, derivative, the quotient rule, you know, and then you get this final answer right here. This is the 1/2 derivative of 1 over 1 minus x. And now here's the thing, like 1 over 1 minus x is clearly is a rational function, is a quotient of two polynomials, and well, the denominator is just 0 order, 0 degree, but it's still polynomial, like a monomial. Anyway, so 1 over 1 minus x is a rational function, but it's semi-derivative. It's 1/2 derivative. It's not a rational function. It has square root and like 1 minus x to the power of 3/2 in the bottom and inverse sign. Like, it's clearly not rational at all. So yeah, it's just kind of like a strange thing for the fractional calculus, fractional derivative. It's kind of cool, right? Well, if you like my videos, please subscribe to my YouTube channel and follow my Instagram math page with the same name, DVKT Math. And thank you for watching.